Okay, what I'd like to start with is the problem of the day. Is this the problem of the day that people have seen, the one about dropping eggs? Or was there a different problem of the day?
That's the one.
This is the one. Okay, so this is a problem I like a lot. So I want people to think about it. I want us to go through it as a prototype of how you work out a dynamic programming thing. Okay, so what is the thing that you have noticed? I'm assuming in the course of you doing business, you have occasionally dropped an egg, and you have noticed that if you drop it from high enough, okay, it will break. If you drop it from someplace very, right near the bottom, it won't break. Suppose we want to figure out, okay, how we have a building, okay, and the building has n floors. And we want to figure out what is the height where eggs break, okay? So you could imagine a world maybe at level, x minus 1, you drop the egg and it stays an egg, okay? At level x, you can imagine you drop the egg and it becomes splat, it makes a mess. Okay, and we're trying to figure out what is this x? What is the smallest height that will cause the egg to break? Okay, any questions about that? You were given a certain number of eggs, and you want to try to figure out where is the transition between breaking and not breaking as efficiently as possible. Okay. Our cost model is how many times we toss an egg off, okay, and that, okay. Any questions about that? So again, what's the important thing? If you drop an egg out and it bounces, you can go down and pick up that egg and test it again later. If your egg broke, you just have a mess and there's nothing to test. Does everybody see? You got to use a different egg for future experiments. Okay, good. Okay, so let's say let's let E sub k n be where you've got an n-story building. This is the building height. And k is the number of eggs. What's the minimum number of droppings you need to find this transition? Okay, so my first question is, can you tell me what E of 1n is? Show me that E of 1n is n. Does anybody, when you got one egg in an n-story building, how many drops does it take to find where the building is, where the transition point, the critical floor?
You start to drop it from the first floor and it doesn't break. Second floor, it doesn't break. And you can keep picking the egg up each time. So then at the floor that it does break.
Right. So basically keep tossing the eggs out of successive floors until you get the splat. And then you know. And if in the worst case, what happens, you toss it off and you find that at the top floor, it still doesn't break, or it does break. Okay. But that's what it is. Does everybody see that E of 1n is n? Can anybody tell me what E of, let's just try another fancy one. What is E of nn? What's the minimum number of tossings you need if you have an n-story building and you have n eggs? What is the most efficient way to do it? I'm hearing someone say 2.
You could split it, like merge sort, or not merge sort. Blanking on the word.
Okay, blanking on the word. The word matters.
You can go halfway.
Binary search.
Binary search. You are saying that if I have n, if I have n eggs, let me try to make this green. You're saying start in the middle and toss an egg. The important thing to see is if we have n eggs, we have enough eggs that we don't need to, we can, afford to destroy an egg on every toss, right? Now the claim is we can do a binary search. We toss it out the middle floor, and if the egg breaks, then the transition point is here. If the egg bounces, the transition point is there. Does everybody kind of get that? So I want to say E of n should presumably be log n. Okay. We may have to, figure out if we round it up or down or what, but it should be clear that it's something like log n. And it should be clear that this should be true even if instead of having n eggs, I have log n eggs, right? So long as I have enough that I can afford to break every one I need in the toss, I will be done. Does everybody see how this works? Okay, now the next part, just to try to think about this puzzle, is let's make it, it's a simple form of the next question. What is it E of 2 comma n? What if I have 2 eggs? How many tosses do I need in order to find the transition point if you're giving me 2 eggs? Can anybody give me a strategy here? This is not dynamic programming I'm looking for here, by the way. I just want you to give me an idea. Okay. Of an efficient way to find the height of the building. Okay. Someone is telling me, drop the egg from the middle of the building. Okay, so one idea might be to drop the egg from the middle of the building. Okay, what happens if I do that? Okay, if the egg doesn't break, that's good for me, I guess. If the egg does break, then what do I have to do? I have 1 egg left. What am I then going to do? Okay, I'm going to have to start from the bottom and crawl it up, right? Okay. So does everybody see that if I do this with the strategy where I drop it in the middle, I am going to claim that if I drop it in the middle by that strategy, I'm going to use about n over 2 tosses, right? Is there a more efficient thing to do with 2 eggs? Okay. I heard one idea on the chat. Again, I prefer my ideas if they are spoken out and yelled at me. But what I'm hearing is instead of doing it, another idea is you start at the 2nd floor and you go to the 4th floor, the 6th floor, the 8th floor, the such and such. Once it breaks, you now know that it's either that was the transition point or the spot below it. So you can use 1 toss from the 2nd egg to finish it. Does everybody see that the jump by 2 strategy also uses n over 2 eggs, tosses? Is there any other way to do this? I am claiming here you can do it in n to the 1/2, a square root n eggs. Can anybody see how to do that? Okay. Any ideas here? How you get square root n eggs? What if I use the skip by 2 strategy? What if I instead do a skip by square root n strategy? So I first go up to the square root nth floor. Then I go up to the 2 square root nth floor. Excuse me. 3 square root nth floor. Ultimately, the building has n floors. The last floor is the square root n square root nth floor, because square root n times square root n is n. Does everybody see that if I do this, there will be a place where the egg breaks? And if it broke here, we know it didn't break at square root of 2 square root n. It broke at square root n. Now I can walk up here with my second egg. So I claim that I will spend at most square root n steps going up in chunks of square root n. Once I have done that, I'm then going to walk up square root n steps one after another, and I will be done. Does everybody see that that proves that e of 2n is going to be less than or equal to 2 square root n? Any questions about that? Do people see it? Okay, I'm seeing nothing, no evidence of this registering. Do people get this divide and conquer idea? That the problem, what you guys were doing before, was you were being either too aggressive in your first toss, okay, which is almost certainly going to cause it to break, or you were being too tentative with the first egg by only going up 2 steps at a time. In fact, you want to kind of balance when you do one of these two-phase things. One of the big principles of divide and conquer is you try to balance the work between the two phases. And that's what I did. Does everybody see that if I give you 2 eggs, you can do this in 2 square root n? Or does someone want it, or is that confusing? Okay. Question? Okay. The next question, now that we have started to warm up the eggs a little bit, the next question is, could you give me a recurrence to compute what E of nk is exactly? Okay. And this is what I want you to do now. Try to find exactly what E of kn is. Okay, for any k and any n. Now, doing this divide and conquer thing, I had to be a little bit clever. I had to say I'm breaking it into pieces, right? Now, let's do a dynamic programming version of this. Okay? So E of k n equals the min number, possible number of tosses to find the critical floor in an n-story building with k eggs. I always start by writing out my function to know that this is what I want to do, compute. Now, can anybody come up with a recurrence relation to compute what E sub kn is? Any ideas how this could possibly go about it? Any ideas? Anyone want to try to work through this? What floor should we toss the first egg off on? Anyone have an idea?
The first floor.
Well, you're telling me that the best strategy is to toss the egg off the first floor. And that's certainly not the right answer, because what you call it? We saw for if k was n, it paid for the first toss to be in the middle. So it was like a binary search. Okay. What I'm going to tell you is the floor to toss it off on is the ith floor. Okay. How expensive will it be if we toss it off on the ith floor? Okay, suppose I have a building and I toss the first egg off the ith floor. how expensive will it be to finish the job from here?
It would be less expensive because you could either just check up or down depending on the result of the egg toss.
You're telling me that once I have done it, I will, sorry about that. This is unfortunate. I hope I get this right now. Once I toss it off on the ice floor, you're telling me, either I'm going to have, no, it's in, my transition point is in the bottom, or I'm going to know it's in the top. Does everybody agree? So what is the number of when I toss this thing off on the ice floor, what is the cost of it? Okay. And I want a recurrence. So this cost had better be in terms of E. Right? If we're doing dynamic programming, you want this to be a recurrence defined in terms of itself. Any ideas of what the cost is if I toss it off on the ice floor? What is the cost if I don't break the egg? Okay. If I don't break the egg, okay, I am going to say that if the egg doesn't break, how much work is left? I've got how many eggs left if it didn't break? I started with K. How many eggs do I have?
If it didn't break K.
And how many floors do I have left to deal with? If it didn't break, then I know that it's safe here. I've got how many floors up here?
N minus I.
N minus I floors, right? And what happens if it did break? What's my problem reduced to? Suppose I
K
tossed
minus
it off
one
and it
eggs.
made a mess. What was the, how much work remains?
We have K minus 1 eggs.
You're saying there's something about E of K minus 1. And how many buildings are there? How many floors left do I have?
I minus 1?
I think I have I minus 1. That sounds about right. Okay. Now, which of these is bigger? If you think about the worst case time, we worry about which of these is bigger, right? Which one of these is bigger? Okay. Can you tell? I claim it depends upon what I is, and I have no way to tell, right? But what if I say max of these two? Okay. Now the cost of doing it is going to be, if I tossed it off on the ice floor, it'll be the bigger of these numbers, plus I claim 1. What is that plus 1 going to be? That's actually making the toss on the ice floor, right? We spent 1 toss. This is the toss that we made on the ice floor. Okay. If we got lucky, we'd get the smaller of these. Either a good thing would happen where we're either going to be rooting for the egg to break or not to be rooting for an egg to break. But if we're worried about the worst case, then I claim, what you call it, the max is what it's going to be. Now, which is the value of I that we should toss the egg off? Does everybody see this is, I believe, the cost of what it will of how many comparisons it would make if we toss the first egg off the ice floor? That I think should be clear. Now, what is the I that we should use? Which is the best I? Okay.
If we go off the previous slide, I think it would be the kth root of n. I'm not sure though.
Okay, so you're saying, oh, I'm thinking about kth root of n. I'm thinking about, okay. I don't want to think about things. I want to let dynamic do. What's great about dynamic programming is I'm not going to want to think of, make sure I know what it is. To say it's that's the right place to do it, you need a proof. What if I say min as I goes from 1 to n of this? Now look at this expression in all its majesty. Okay? What is it saying? For the optimum way to toss k eggs, there's going to be a first toss. If I toss it at position I, the cost is going to be one toss plus the bigger of the two situations. If the egg breaks, I'm in this world. If the egg doesn't break, I'm in this world. What is the best possible I? Well, I'm going to try them all. Do you see? That's what the great thing about dynamic programming is. I don't have to be clever and tell you what the answer is. I want it to fall out of my dynamic programming thing. It's clear that the floor I want to toss it on is the one that will minimize the worst case work. If I try all I, then I will find the one that minimizes the worst case work. Any questions about that? How many people sort of see it? Why are we taking the max? The max here is because we are looking at the worst case thing. Suppose we wanted to do the best case thing. What would be the best case strategy if we're given a certain number of eggs in a building of n floors? What is the best, if we want to make it so that if we're extremely lucky, it takes the smallest amount of time, what would be the thing to do?
Take the
I claim
minimum
it would
instead
be
of the
the
max.
toss. Yeah, what would be the best thing then?
Take the minimum instead of the max.
No. What if I toss it off the first floor and hope it breaks? Everybody see, if I toss it off the first floor and it makes a mess, I'm done. So I want, this is a thing about the worst case. I want to guarantee that after a certain number of tosses, I am done. What am I going to do? The worst case time, I'm going to pick the best I by the one that minimizes the worst case time. The worst case time is going to be given by, there are two situations, and one of them is probably more expensive than the other. If the egg god was trying to make me work as hard as possible, they would always decide to either break or not break the egg based on which one of these sides was bigger. Max is the worst case part of the amount of work. I presumably want them to be about the same amount of work. To minimize the maximum, I probably want the two of them to be about the same. Okay? But I don't have to think that through. I know that I'm going to minimize the maximum this way. Any questions about that? Okay, so it's the best of the worst case scenarios. Any questions now? Preferably by voice. People kind of get it? If you get it, what is the running time of this algorithm? Okay. Can anybody give me an idea of what the running time of this algorithm is? How do we compute the running time of a a dynamic programming problem? What is the formula for it?
Should be number of boxes times
Number of
work
boxes
done.
times what?
Work done at each box.
Okay, how many boxes are there? If I have a building with k floors and n, and n floors and k eggs,
K times n.
does everybody see that this is going to be the running time is going to be the number of boxes times the time per box. The number of boxes is going to be k times n. Now, what is the running time of filling this box? Can anybody tell me what this is?
Looking up the indices is constant. Addition is constant. Finding the max is constant, and then we do that over n.
Okay, so this is right. Look this guy up in a table was constant. Constant. Take the max of two things was constant. Add 1 to it is constant. Now we're doing that constant time operation n times. Does everybody see that it is order n time per box? And this gives us an excellent algorithm that runs in kn squared time. Any questions about that? Any questions of where the running time is and how you work out the running time?
Yeah, could you go over one more time why the time to fill each box is order n? I missed that a little.
Well, let's look at what work you're doing. Okay, let's think how you would program this. Think about how you're programming this. This min thing is presumably a for loop that's going, I goes from 1 to n. Try every possibility, right? So this is a loop going around n times. Within the loop for a given I, it's look this element up in a table, look this element up in a table. How much time? Take the max of two numbers. What is how much time does it take to find the max of x plus y, x or y? Takes constant time. Takes constant time to add 1 to it. It looks to me that this takes something like 1, 2, 3, 4 computrons, okay, per per time the loop goes around. Certainly it's a constant number of steps for each time this loop goes around. So that's why it's n. If you want me to say is it order n, that would probably be the more accurate way to deal with, say it, describe it, right?
Gotcha.
Put a big O of n there. It's not n exactly, but it may be 4n or 65n, who knows? Okay? But this is order n, and that's why we get the order kn squared. Any questions about that? Is there anything else on this recurrence that we need? Are we all done now?
What order do we fill the boxes?
What order do you fill the boxes? Okay, well, that's a good question, and maybe we will look into that. What I was hoping you were going to say first was you need to know what the initialization conditions are, right? What are the boundary conditions for your recurrence? Does anyone have any boundary conditions that they want to think about? Okay. We need, I claim the boundary conditions I probably care about are what? Of 1, comma n. This we kind of know was n, right? The only other case that I'm wondering about that's probably interesting is what do we know about where you've got what is E of k eggs and a 1-story building? You know how much that's going to cost?
One.
I think that's 1. That looks pretty good to me. So now let's look at that table that we're going to fill in. Again, I hate erasing anything. I don't know if you guys like me to erase things, but let's think about what our matrix is going to look like. our matrix, if I understand it right, actually, oh, you guys don't see to the, do you guys see to the bottom of my, my square there? Let me just look this up.
I see the whole square.
Good, you see the whole square. So my egg side is going to go from 1 to k. My, floor side is going to go from 1 to n. When I've got one egg, okay, and a floor with n things, this was going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, ... n, right? When I have one floor and I got enough eggs, it's all going to be ones, right? Now I need an evaluation order for this thing, right? My claim is, in both cases, if you look at this thing, the number of eggs kind of, one case goes down, in one case it doesn't, okay? In general, though, in both cases, the floor sizes get smaller, right? So I'm going to claim I'm going to want to fill in my boxes like this. And in general, to fill in a particular value here, which was k, kn, if I, if I want to think about this thing, what am I going to be looking at? Well, for any given I, I'm going to be looking at, for any given I, I'm going to be looking at I minus 1, k minus 1, which is going to be a number like that. That's going to be, I know here I've made it too small. That would be I minus 1, k minus 1. And I'm also going to be needed k minus 1, n minus I. So if this was n, there's going to be another place that's going to be the n minus ith one. And for k minus 1, it's going to, for k, it might be this cell. Does everybody see that the two cells that I'm looking for are to the left of where I am now? Do people see that in any way? Okay. If so, then I can fill this thing up going down columns. And whenever I fill this thing up for any I, the two numbers I need are basically waiting for me. Okay. Any questions about that? Any other questions about about the egg problem? Going once. See, I like this. Yeah, question.
So what's the solution? Would it be at the k-nth box?
Oh, you mean what is the solution? You mean how do I find where I'm going to toss these things?
Oh, yeah, yeah.
You're telling me how many tosses it is. You're saying, oh, but I'm not telling you actually where the tosses are, right? So what was the answer there? That's a good question. Well, originally, again, in general, I am going to be interested in the height of the building and the number of eggs that I have. This is my starting point, right? This is really a cost matrix. I should also keep track of a parent matrix. And the value then of this cell at Kn should be the I that minimized this. Does everybody see that when I did this min, I was basically figuring out, discovering which was the I that was the best place to toss it in. The best I was going to be the I here. So if I stored this I in this cell, This is going to tell me where was my first toss going to be. Okay. And then, okay, once I've done that and I learn whether it went splat or not, knowing that I chose it for I, if it went splat, I went here. If it didn't go splat, I went here. Do you see that once I did that, there would be another cell I would go to? Okay, if it didn't go splat, okay, my next move might be, if it did go splat, this would be k minus 1, I minus 1. And maybe in this cell, it'll tell me the next place to toss my my egg, which might have been at floor 5. Okay, so you see that in order to reconstruct the order, this is an important thing. In order to reconstruct the order of what my tosses were, I needed to keep track of what were my decisions at any given point. And then to play through this on any building, this matrix is going to encode the strategy for the optimal egg tossing. And I just have to throw the egg out on the appropriate thing, and it's going to be there. Okay? Any questions about that? That's a good question. Again, in the edit distance problem, which you looked at, the edit distance problem, the kind of previous move, where did you make those substitutions? You had to walk back through the parent matrix, right? That described the path that we talked about last time, back to the root. It's a similar thing here, okay? So typically there is a cost function that is going to help us make the right decision. And once we know what that decision is, we store it up in the parent matrix. Any questions about that? Any other questions about this? Okay. Now, some of you are saying, okay, there's a question here, is this a typical dynamic programming problem? It's a typical dynamic programming problem in that there is an array of boxes and that there is a recurrence to fill the boxes. And once you learn to think about it, this is not an incredibly complicated expression. Okay, it may look a little bit ugly to you now, but if you look at how many terms this thing is, okay, once you think about this the right way, you realize, okay, I'm going to be taking the maximum of 2 possible. This solves the, hopefully you can formulate a recurrence for this. So the 2 parts of dynamic programming are 1, formulate a recurrence, 2, figure out the cost of solving that recurrence, okay, by storing the results. Any questions?
On the test, will we have to give the initialization conditions in order to fill the boxes?
Well, okay. It's always good karma to give the initialization conditions. Okay, so you should give the initialization conditions. If we don't take off because you didn't have the initialization conditions, it's probably because we neglected. Okay.
Okay.
So you should have figure out what the initialization conditions are.
Sounds good.
Okay. But typically when I ask you for a dynamic programming algorithm, what am I asking for? I am asking for the recurrence and presumably the initialization. And when I am asking for a runtime analysis, I'm asking for typically number of boxes times time per box. Any questions? Okay. So basically there is, in principle, usually either 2 matrices, the cost matrix and the parent matrix, or in the code I used for my dynamic programming, my edit distance, I actually combined them. I had was 1 table of records where each entry had both a cost and a parent. Okay, so it's conceptually 2 tables if you think of it like that. Any questions? Okay, let me give you a simpler dynamic programming problem that I once solved that is actually relevant to your life. If you pick up, many of you have driver's licenses. Pull out your driver's license. And if you look on the back of your driver's license, you probably have something like this on the back of your New York driver's license. Can anybody tell me that they've got that? Okay. Look at your driver's license. I'm going to take, I want to take a look at mine. Does everybody have this kind of thing on their driver's license?
I got one.
Okay. What is this? Does anyone know why this is on your driver's license? Okay. This is because this is basically your prison record, if you want to know what's there. Okay. That that the police, when they pull you over for no doubt a well-deserved ticket, okay, will ask for your license. They then want to go back to know who are they dealing with. Are they dealing with somebody who is, a dangerous person or a normal person? Okay, it would be good to know. So what do? They basically encode your prison record in a label like this. And they have a barcode design that was produced by a Long Island company. This company is now Zebra. Okay, if any of you have ever heard of Zebra, which is, not far from Stony Brook. Okay, they developed this barcode technology, this two-dimensional barcode technology, so that you could scan, quickly scan with a label and read a lot of information in it. So they wanted a barcode that could hold several hundred bytes. And in order to do this, they developed a text compression scheme. Some of you guys have long prison records, but you still have a small, driver's license. You'd like to pack that information as tightly as possible. So what did they do? They developed this scheme for, encoding text, where they came up with 4 sets of the alphabet. Okay, of different letters. Here they had the capital letters, A, C, B, D, Z. Here they had the lowercase letters, A, Z, okay, A, B, C, Z. Here they had the punctuation symbols. Here they had the digits and the punctuation symbols, okay? And they may have had a couple of important punctuation symbols here and a couple of important symbols there. What was the question? Now, you guys should know, actually, we talked about logarithms, and we know that if you have k bits, you can represent 2 to the k different numbers, 2 to the k different possibilities. Normally, to encode a text letter, okay, you might use 8 bits. If you used classical ASCII, you would use 8 bits per symbol to encode your prison record. Okay? These people said, I'm going to be smarter than that. I'm going to put 32 characters in each block, okay, or about 32 characters in each block, okay, so that instead of sending out all 8 bits, I only had to send 2 to the 32 or 5 bits. And if your message is, capital watch for this guy, exclamation point. What the way to encode it is get into the capital uppercase mode, then type out all these letters, and then go into the punctuation mode for this guy. He is trouble. Okay. The right thing you would like to do is to go and go permanently, at least for a while, into the capital mode. Print out the capitals at 5 bits per letter. When you add an exclamation point, if you were only going to use it once, temporarily shift into the issue 5 bits to shift into the punctuation mode, and then jump immediately back. Okay? And then you'd be back in the, and then you could do these at 5. Recognize that if you've got a name that is, so the question is, you've got the letters in different modes. You pay a price for jumping from one mode to another. You can either shift in one step to a mode, so you go temporarily into a mode and then jump back to where you were, or you could permanently jump into a mode. So if I had things from lowercase, the report, if it was lowercase, I'd like to be in lowercase and here permanently jump into the next mode. Or if it was a word like the capital W-A-T-C-H, I'd like to temporarily go into that. So if you understand what I'm saying, to encode any message, there are different costs depending upon what mode you jump into, okay? And whether you're going to jump in permanently, which is a latch, until you have another latch command, or temporarily, a shift will jump in for 1, okay? And you don't have to jump back. So this is the scheme that is encoding your license plates, your driver's license report. And when they showed me this thing, I said, my God, there's so many different ways for you to represent any particular string. You could jump from one mode to another. How do you know you jump to the right modes? And they said, well, we just, I don't know, we tried something. It's a heuristic, it's good. So I said, well, why don't we do this by dynamic programming? Let's think at what is the minimum, let Mij be the cheapest possible way. We have a text of length n, from 1 to n. And there are k possible modes, j possible modes. Okay? So it could be the number of modes. In this case, went from 1 to 4. What do I want to know? I probably start out by default in one mode. Okay? Now, what is my goal here? My goal is to figure out for a given prefix of the text, okay, up to the ith character, what is the cheapest way to encode it, okay, ending up in mode J. That's what this is asking me. What is the cheapest way to end up in mode J, okay, after encoding the first I characters? I claim this is the min over all modes k from 1 to 4 of the cheapest way to encode the first I-1 characters of the text, ending up in mode k, okay, plus the cost of going from here to output character, the character that's in the ith position, okay, and ending up in mode J. So this might be latch into mode J and output the code. It might be, output node the code and then jump into mode J. There is, I claim, once I am at a point where I've encoded the first I-1 characters in mode K, there is an easily obtained cost to go from here to outputting the next character and ending up in a mode. My claim is the optimal way to encode it is the optimal way to encode the first I characters ending in J is going to be the minimum over all possible modes of the best way to encode the first I-1 characters ending up in mode K, plus the cost of dumping out what was the ith character of the text and jumping to mode K. Any question? Do people kind of see this thing? I claim that in order to find the best way to end up at to end up having dumped out the first I characters ending in a particular mode. Well, I had to find the best. It would have involved the best way to output the first I-1 characters ending in some mode, plus the cost of going from that thing to the last character. Okay, and this is essentially a table lookup. This thing at the bottom. This is a constant time thing. Okay, any questions about that?
So in other words, it's determining which mode you should be in before mode J that is the cheapest to get to mode J?
Which is the mode that I should be in to minimize total costs. Ideally, it might have been in mode J before. If I was in mode J before, all I have to do is output that one character. If not, I have to pay the cost of switching modes and outputting the character. But sometimes that's a good thing. Okay?
Okay.
So this is going to make the decision. The dynamic programming thing is going to make the decision of when I swap from one to another. Okay? Any questions about that? What is the running time of this algorithm? If I have a text of length n, and let's say that there are let's say that there are j different modes. Actually, j is going to be equal to 4, but let's leave it as far as j goes. How many boxes do I have? Okay. How many boxes? Times the time per box. Any questions about that? How many boxes? Does anyone see this thing?
NJ.
What?
Number of
N
boxes,
times
NJ.
j boxes, right? Length of my string times the number of modes. How much time per box?
J.
This is going to go around j times, and it's going to look something up and do a local thing that involves one character. So there's no, there's nothing really magical. So this is going to be j times 1 or j. The total time of this algorithm is order n j squared. Any questions? People kind of see what this is doing? Okay. Basically, if we think about it conceptually, to fill this cell, I am going to presumably be looking at all of the cells in the previous row. Okay, I have one possibility coming from here, one possibility from here, one possibility. Okay. Any questions about that? And when we did this thing, again, I visited this company and I said, you guys use dynamic programming. And when they just switched to our dynamic programming algorithm, they got labels that were shorter than, they were proud of what they were doing, but my labels were the minimum possible size with their code. And and mine were 8% smaller than their guys. So you guys can accumulate an 8% larger prison record, okay, without needing to get a bigger driver's license. So I hope you guys thank me for that. Any questions? Okay, there's a question of why is the time per box j? Note that this minimum, actually, I guess what I'm saying here is, actually, the trouble is I've reused j a couple of times. Okay, let's maybe do it again here. Let's call it q. Let's say that there are q modes. Okay, now q happens to be 4 in the example I showed you. But what would it be? If there's a total of q modes, okay, actually this would still be j. To compute m sub j, any of these things, there are, okay, n times q boxes total, because the position in the string can go from 1 to n. I guess if I did this to ij, that's probably the right way to do it. I can vary from 1 to n. The number of modes can vary from 1 to q. This is going to go around. This is, say, q, it goes, here, k equals 1 to q. This is going to go around q time. And this would now be nq squared. Does that answer the question? Any questions about that? Any questions about any of these dynamic programming things? Okay. Let's see if, okay, so I'd like to, let me decide how I want to do this now. There's another example which is kind of complicated. I don't want to do that now. Let me try a simpler dynamic program. Again, 9 minutes from now, we're going to have a test of the HonorLock browser. So I encourage you all to download your Google browser if you haven't done so. But let's look at something different. Let's look at a very simple very famous dynamic programming problem. Let's say that I have a DAG that is topologically sorted. And I want to find I have a DAG with n vertices and m edges. Okay, and I want to find the length of the shortest path from S to T. Everybody see, it's going to consist of, there's going to be an edge from here to some other vertex, maybe from here to a vertex, from here to another vertex, maybe there's going to be another one like that. Does everybody see what I'm doing now? I have a topologically sorted DAG. So all the edges go from left to right. And I want to find what is the shortest path from S to T. Okay. I could do this by, my Dijkstra's algorithm or something like that. But let's try to do this by a dynamic programming idea, just to make sure we understand, because this is kind of a basic thing like this. Okay, let's let D sub K is going to be equal to and let's say these are weighted graph edges or something like that. The minimum size path from S to K in a G. Can anyone tell me, if this is vertex K, what is a recurrence for what the cost of the cheapest path from S to K is? Can anyone think of such a thing?
Wouldn't it be the paths from everything leading up to it?
Everything
plus
leading
those
up
lengths.
to it. Okay, how would I write this?
D of k minus 1.
You will say it
plus,
depends on k minus 1, but now, no, wait a second. I don't know if I believe that. If you look at this graph, there is no edge from k to k minus 1. Right? Is there necessarily an edge from vertex
well,
k?
yeah, I meant like, so I guess it would be the minimum of d to k minus I plus the length.
Well, I have a graph. These are vertex numbers, v1 to vn. Okay? I claim that the shortest path ending in k is going to have what as a property? What's the last edge on the shortest path from S to K? It's going to be from somewhere, right? I claim that this should be equal to the min as J less than K of D sub J plus the weight of the edge from J to K. Okay? Think about this. Suppose we know it's a DEG, so all the edges go from left to right, right? If you want to find the cheapest path to K, there had to be a last vertex that you were using, right, on that path. That path, that edge is going to be some edge J. And if we do that, what's the cost of that path? The cost of getting to J plus the cost of that last edge from J to K. Does everybody kind of see that?
If edge JK doesn't exist, should the cost be infinity?
Yes, so if edge JK doesn't exist, then the cost is infinite, right? So that's 100% right. Okay. Now, do people see why this has to give us the correct answer? Because we know that the shortest path from S to K is going to, okay, have a last edge. That last edge is going to be some vertex J that appears before K, because this is a DAG. Okay? How do we know which the best vertex is? The best vertex is when it defines that, right? So what is the cost of this algorithm? What is the running time of this algorithm? It's a function of how many boxes times the time per box. Okay? How many boxes are there in this recurrence on an n vertex and m edge graph?
N?
N boxes. How much time does it take to fill each box?
If K is N, I think worst case would be N minus 1.
Okay, does everybody see that we're going to be looking at all indices less than K? So this is going to be order N. That's the worst case time. This would give you an order N squared algorithm for this. And actually, if you're a little cleverer about it, okay, and you actually had just had the adjacency list of all the edges that went into D, you could only use the vertices that actually have edges. Okay, there's actually a way to do this better for a sparse graph. But does everybody kind of see that how this recurrence works? This is now a really simple recurrence. Okay, and it would find the shortest path, okay, in a DAG. Any questions about that? Any questions at all? Okay, so at this point,